Okay. How are these going, these angle properties? Do you remember some of them? Great. Okay. Folks, 7.1. Congruent and similar triangles. We're trying to match these up. So, gotta unlock the screen here. All right. When two lines intersect, the blank are equal. Oh yeah, that's like this. Maybe you might call it an X pattern. It's like, okay, angle A is equal to angle A, and angle B is equal to angle B. And what do we actually call these? We call them opposite angles. Now, the angles opposite the equal sides of a blank are equal. Of what? What is this? This is an isosceles triangle. And what it's trying to tell us is, yeah, we know isosceles triangles, even from our second unit in this course, the coordinate geometry. We know that the two side lengths on an isosceles triangle are equal. But if you look a little bit deeper into these properties, it means that this angle here is equal to this angle down there, because they both open up to create that same length of the side. So like this angle here opens up and creates this side length over here. And then the other side has got to open up at the exact same rate to create the side length over here. I'm sure you've seen that before. What do we call these when they add up to 180? Supplementary angles. C plus D equals 180. It's kind of impressive if you've remembered like what they're called. Like I know I can give you this question, you know what's going on, but to remember the precise name is kind of challenging. Does anyone remember this one? They add up to 90? I think if this is supplementary, I think this is complementary. Yeah, complementary. All right, this one over here. The sum of the blank in a triangle is 180. Now be careful here, because there are different types of angles that exist, and I think in this one we're talking about interior angles. Because if we're talking about exterior angles, it would certainly be not 180. It would be, I think, 360. Okay, maybe you might have seen a lot of this stuff, the first 5 here, maybe from grade 8 a little bit, certainly in grade 9, but again, I don't know how much time you spent on that. Definitely not a lot. Definitely not a lot. And here we have a transversal. So when they say the word transversal, what they're talking about is this diagonal line, right? This blue, in most cases, that blue diagonal line, that's the transversal. So when a transversal crosses parallel lines, so you'll see here these parallel lines in each scenario, many pairs of angles are related here. So first we have this Z-looking pattern. You see how I highlighted that Z on there? And we call them alternate angles, such that it's like the armpit of the Z. Those angles would be equal to one another. So I don't know if you want to put like an X and an X there. Those angles, that armpit of the, I call it the armpit, I don't know. What do you call that? That part of the Z. Then we have this F pattern going on. The F pattern is called the corresponding angles. And again, it's very similar to the Z pattern where it's like underneath, again, kind of like the armpit of the F. Now, I feel like those are the most common types of angle properties you see. Sometimes this one may or may not come out to play. Usually, it's not a ton of stuff. It's not a ton of scenarios where you'll see this this last one here. But I think we call these the co-interior angles, which is kind of nice that it's called co-interior because it's a C pattern. And it's not that these angles are equal to one another. It's that the A and the B, right, the armpit of this C, the A and the B add up to 180 degrees. So like at 170, the other one's 110, Does that kind of ring a bell? Like if it kind of rings a bell, I think we're in good shape. Like I said, for the most part, we're going to be really looking at the corresponding angles and also the alternate angles. All right. Folks, first let's talk about congruent triangles. And based on that little diagnostic we had here, what was your sort of definition of a congruent shape? Do you have one? Yeah. What do you got? Yeah, it's the same shape and it's the same size. In fact, it's almost like you got one shape and you've copied and pasted it and maybe turned it a little bit, right? It's almost like the exact same thing. So when we talk about congruent triangles specifically, it's a pair of triangles that have equal corresponding angles and equal corresponding side lengths. So you know what? I'm actually going to use your definition at the end here, and we can say it's the same shape and it's the same size. I like that. Now, I'll give you a moment to write that down. Okay. Now it says here, for example, triangle. See how they write? See how they write this? Triangle ABC. A. So you start at the top. A, B, C is congruent to triangle F, D, E. So a lot of the times, especially the textbook always kind of sets us up nicely for this. When you're talking about a pair of triangles, the order in which they're kind of expressed kind of shows you that, oh, the first one, angle A here, will correspond with the first one, angle F. We would call them corresponding angles because it's like whatever angle we're talking about, it's in that exact same order when you write them down. Like really, I wanted to write DEF, but DEF would not be right to express this right triangle over here because we want to follow ABC. So it's like top. See this? It's like this direction. So we had to go FDE. So if these triangles are in fact congruent, let's say, you know, let's just pretend here. Let's throw in, if they're congruent triangles, we can say, this is like 70 degrees. This is 70 degrees, which would mean the top would have to be 40 degrees. So that also makes sense. And let's just say they're isosceles. Let's say this is like 6, and this could be 4. Probably won't really add up quite well, but I'm just doing this on top of my head. So you could even say like millimeters. Now, since this example expresses the fact that these two triangles are in fact congruent, what we know about this triangle is that, okay, this angle A is 40, so that means this angle F must also be 40. Yeah? And it says B is 70, so that means our D must be 70. And likewise, we have a 70 down here. Now, another cool thing is that we can kind of look for the corresponding side lengths. So AB, right, the first two here, AB would correspond with FD. BC would correspond with DE, and CA would correspond with EF. And I know we're talking about congruent triangles here. It almost seems like that's a waste of time to use 3 different colors to outline that, because I know that you and I can both just see that this is going to be 6, which means this is also going to be 6, which means the bottom here is going to be 4, right? Because they're congruent triangles. They're going to have equal corresponding angles and equal corresponding side lengths, or what we can say is it's the same shape with the same, it's literally the same triangle copied and pasted. So we represent congruency with this symbol here. It's like an equal sign with a little squiggle on top. That squiggle's name is tilde, but that's the sign for congruent. So therefore, we can rewrite the congruency statement as, like, instead of saying triangle ABC is congruent to triangle FDE, we can say triangle ABC is congruent to triangle FDE. Does that make sense so far? Congruent triangles? Like a couple years ago, we actually used to go super duper in depth with congruent triangles, and I don't really know why, because the textbook really just touches on it a little bit, and then that's kind of it, or rather I should say this new textbook. Questions about congruent triangles? Pretty much as far as we need to know, they have the exact same angles with the exact same side length. Okay, now, this is where we come up with similar triangles. See, congruent triangles is the same triangle twice. Now, I'm curious, on that diagnostic, what did you have for the definition of similar triangles? Because it had to be different from the congruent triangles. Yeah, what do you think? Same shape, but different size, I guess, right? So, what do we have here for the real deal definition? There's a pair of triangles that have equal corresponding angles, okay, just like the congruent, but here's the major difference. It says it has proportionate corresponding side lengths. Proportionate. Do you remember the word proportionate? Remember ratios like 1 to 2, 1 to 8? Similar triangles is pretty much that. It's pretty much just a giant ratio between the pair of triangles. So I thought I had, oh, I did equilateral? Maybe let's not. Okay, now what do we mean by proportionate side lengths? Okay, so we have your triangle ABC is similar to triangle XYZ. And notice again, ABC, XYZ. They're in that same nice order, and they usually should be. They should be. Let's go ahead and maybe use the exact same angles we did over here. Let's go 70, 70, 40. Yeah? Now, in order for triangles to have the exact same shape, it means that the corresponding angles must be equal. So, for example, angle A is 40, which means angle X must also be 40 degrees. Oh, I didn't put little degree symbols. Likewise, if angle B is 70, that means angle Y must be 70. And if C is 70, then angle Z must also be 70. Now, so far, congruent and similar triangles have the same characteristics so far, right? They all have those equal corresponding angles. Now, here's where similar and congruent differ. If this were, for example, 6, and this was also 6, and this bottom here was 4, I don't know, meters, let's go with meters this time, then how about I give you that one? Yeah? And how about this one? And how about that one? Oh, I'm doing centimeters. Come on. We got to keep it all the same. So we got 3 meters. Oh, okay. 3 meters and 2 meters. Would this still work? What do you notice between the two triangles? Or what do you notice between the pair of triangles? You notice anything? Yeah. Yeah, all the side lengths, you say, are divided by the same thing. Yeah. So if we're going from big triangle to small triangle, we can say that there's a scale factor. Yeah? So there's a scale factor. It's almost like we're dividing by 2. We're dividing all of the side lengths by 2. It's half of that triangle. Now, hey, what if we're going this way? What if we're going from the little one to the large one? It'll be taking those side lengths and timesing them by 2. Now, this scale factor is what we mean, is what we're referring to when we say proportionate corresponding side lengths. They're in proportion. They're all 2 times big, or you can look at it and say they're half as big. That's what we mean by proportionate. Now, again, if the side lengths were equal, they would be then congruent triangles. But because they're just proportionate to one another, like a times 2 or divide 2, we can say that they are similar. So what we get here is the same shape, but we have a different size. It's almost like Dr. Evil and Mini-Me. You guys know what I'm talking about? No? Oh man, I'm old then. Austin Powers? No one? You know what I'm talking about? No? All right, you guys got some homework tonight. Okay. Now, we often represent similarity by using this symbol right here. It's just tilde. So we can rewrite this as, we can say, well, triangle ABC is similar to triangle XYZ. So instead of writing the whole word similar, we could just use tilde here. Now, there's a little bit to add here, because we got to talk about, and this will become very important today, tomorrow, and for all of similar triangles. It's kind of noticing when triangles are similar. So there's 2 kind of scenarios when triangles can be similar. So the first rule we have here, I'll put a number 1 here, is called angle-angle similarity. That's what we call it. So maybe we can even write that. Angle-angle similarity. So what does angle-angle similarity really mean? In fact, this is probably our strongest weapon. Folks, if we have any 2 triangles, okay? If we have any 2 triangles. Now I gotta kind of make sure I do this properly here. So let me grab a calculator. Let's pretend we have this guy here. Yes? Does that all add up nicely? It does. So let's just say we have this triangle here, then we have a similar triangle, like a similar scalene type of triangle. Or actually, let me back up a minute. Yeah, that's what we want. This is what we want. We are trying our best to make them look similar. Okay, we got 1, 10, and 20. These are the angles. We should put a little degree symbol here. All right, so angle-angle similarity, what does it really mean? Well, it means if you have 2 equal corresponding angles. So for example, 110, 110, we're really happy about that, right? 20, 20. We can then say these 2 triangles are similar for sure because of angle-angle similarity. The reason why we're okay to do that is because if this is 110 and this is 20, this third one must be 50. It must be 50. It has to be 50 because all of the angles in a triangle add up to 180. Likewise, if this is 110 and that's 20, okay, sure, this has to also be 50. It has to be. So we don't really have to look at all 3 of the angles. We just have to make sure 2 out of the 3 are equal to one another. Because if 2 out of the 3 are equal, then that just means that 3 out of the 3 are going to be equal. Because they all have to add up to the same thing, which is 180 degrees. So that's angle-angle similarity. It's super great. It's a wonderful weapon. And it's something that we're really going to use and abuse a ton of. Now there's one more weapon that we have, and it does come in super handy sometimes, and it's called side-side-side similarity. So side-side-side similarity, let me write that down. It's very similar, it's all kind of similar to what we did above here. Like, let's just grab two scalene triangles again. That look all right, kind of. And let's go like this. And then over here, we'll do something like, yeah? Some of you are so clever. You're looking at this, you're like, I see what's going on here. I see it. So we have like A, B, C, and then we have X, Y, Z. Yeah? And what's going on here is that, well, I think you could see it. Do you guys see a scale factor going on here? Do you see a little bit of a scale factor? Yeah? Yes, getting some thumbs up. So what that tells us, well, the first thing you do in similar triangles is you just match up your corresponding sides. You're like, oh yeah, AB matches up with XY. Okay, great. BC matches up with there. And CA or AC matches up with XZ. You can totally see that, am I right? It's all good? So when we're talking about side-side-side similarity, we actually don't have any angles to discuss, or even any angles to prove that these two things are similar. All we have are sides. Okay? So what we want to do is set up our corresponding side length ratios, which sounds like a lot, but all it is this. So we'll do the small triangle on the top, and we'll do big triangle on the bottom. I'm going to keep that there, just so I know what's what. So we have AB, and AB corresponds with XY. Small triangle, big triangle. So we know AB, which is yellow, corresponds with the other yellow, XY. BC corresponds with YZ. And I left a space there on purpose. And we have CA, which is orange, and that corresponds with ZX. So if we go ahead and fill in these blanks, like let's see what we get here. We get like AB is really 2, XY is really 6. So BC is green, so let's pull out green. We'll say this is 5 over 15. And the orange one, we got 4 over 12. Now what happens is that we're able to reduce each of these ratios. So like 2 over 6 is really 1/3. 5 over 15 is really 1/3. And 4 over 12 is really 1/3. You see that? These are all, and I'm going to do this in red, these are all equal to one another. They should, in fact, be all equal to one another, because that tells us, now you can probably just see it because you're clever, because you know, 2 times 3 is 6, 4 times 3 is 12, 5 times 3 is 15. You see what's going on here because you're really clever. But sometimes the scale factor won't be as obvious as timesing by 2 or timesing by 3. Sometimes it's like timesing by 2.81. It's like, woo. So sometimes setting this up will be really good in the long run. Yeah, for right now, you're like, what are we doing? But maybe in the homework or in the long run, for sure. So again, to reiterate, angle-angle similarity, it's really good. Side-side-side similarity, super helpful as well when we don't have the angles. Okay. So the difference between similar and congruent, if not already reiterated enough. So we have triangle RST, and we have triangle JKL. So angle S, I mean, you can see it on the diagram, angle S, right up here. Which angle does it correspond to in triangle JKL? Well, it's going to be angle K. It's going to be K. Not only because it's in the center, right? They're both center like that, but also you kind of just see it on the diagram a little bit. How about angle J? Angle J. Well, that's going to probably correspond with angle R. And also, J is here, R is here. How about the side length RS? This one right here. This side length must correspond with this one here, JK. Then they say, how about RT? RT, all right, that's going to stay there. RT corresponds with JL. And if that's the case, then this last side length must correspond with that last side there. Okay, they want us to kind of create little symbols in here to show the corresponding angles. So how about we do like an X for this angle down here. We'll do an O for this angle up here. And then we can do like a colored in O for this angle down here, just to show that they all kind of correspond to one another. Now, when we're talking about ratios, again, you keep one triangle on top, like you could say, okay, triangle RST is going to stay on top, and triangle JKL is going to stay at the bottom. And you have to kind of be consistent here, like you have to. You start mixing things up, it gets a little wish-washy. So, RS, which we have as the yellow side, corresponds with JK. And that ratio is going to be equal to, well, RS ST, which is the red, will correspond with KL. And lastly, if we go this way, from T to R, and that will correspond with LJ. Now again, it's important that you keep one triangle on top, all the side lengths for that one, and the other triangle on the bottom. Question? Sure. That's similar. Now when we're talking about congruent, all right, here we have congruent triangles. It's like, are they congruent for sure? Now when I look at this, I'm not too convinced that they are congruent. Are you? I don't know if I am or not. So maybe there's a little bit of work to do. So we have 65 and 65. We're like, okay, sure. Then we have here 60, and the other one doesn't have a 60. Here we have a 55. So sometimes the best thing to do is when you have two of the angles, just solve for the third one. So I'm thinking I'm going to do something like 180 minus 65 minus 55. And that equals 60 degrees. So this has to be a 60. And if we go back to the green one, I'm going to do 180 minus 65 minus 60. And that equals 55. So that means that this third angle here is 55 degrees. Interesting. So notice how all the angles are the exact same. And then the corresponding sides, look, we have a 4, a 4, a 5, a 5. They got to be congruent. They got to be. They're the same shape because they have all equal corresponding angles, and they're certainly the same size. All right. So now we're getting really into it here. I feel like we have a good idea of what similar triangles are. So it says here, explain why you can conclude that triangle ADE, so it's like this one right here, ADE, is congruent to triangle ACB. That one there. You see the two triangles, one's kind of nested within the other? Well, we have these parallel sides, so that's kind of nice. Anyone see any equal angles? Any angles that are equal to one another? See any angle patterns? Like if we go back to that first page, You see any angle patterns here in these bottom ones? Because if I look at this closely, you see the upside down F pattern there, which means that angle C would be equal to angle D. Oops. You see that there? So we could even say like, okay, we know that this angle is equal to this angle. And all we really need is one more angle. In fact, there is a common angle between the two triangles. Even if you look at the name of the triangle, they both have a matching letter. Do you see the matching letter that they have, that they share? It's letter A. So what we can say is our statement, the first thing we could say, do I have it already in here? Let's see what I got. No, I don't. Lovely. We can say that angle A is quite literally equal to angle A. And the reason why we can say that is because both triangles share that angle. So we can call it a common angle. It's common between the two triangles. Like, look, ADE and ACB. They have the exact same angle. Then what we also noticed was that, now, when you're stating angles, I would not mind if you said angle D and angle C, but some people don't like that too much. They want to be very specific, because if you're talking about angle D, some people don't know if you're talking about this one here or this obtuse one down there. Right? How do you know which one's angle D? I mean, I think I would know if you wrote angle D. I think I'd know exactly what you're talking about. But some people would rather prefer this. They'd call it angle ADE, because it creates that angle where you can actually see it. Angle ADE is equal to angle ACB. And the reason why we're okay to state something like that is because these are what we call corresponding angles. So then, once we have two out of the three angles, we can say, okay, therefore, triangle ADE is similar to triangle ACB because of angle-angle similarity. That's what we would say, just because of angle-angle similarity. Now, proving triangles are similar is so important, because you won't be able to solve anything unless you can prove that they are similar. Now, this is what the homework's going to be like here. How about, sorry, any questions about that? Does that seem okay? Some of you might say, well, couldn't we have just done angle AED and angle ABC? Like this, yeah, you could have chosen those two and ignored the angle A altogether, for sure. As long as you have two out of the three, life is good. So how about this one here? We have ACB. ACB is similar to EDB. EDB, okay. So we're looking for equal angles. The first thing that my brain goes to is this right here. Do you see this X that's happening right there? It tells us that angle B is equal to the other angle B. So that could be kind of misleading. Angle B is equal to angle B. It's like, what? Well, really what we mean is ABC, like that angle B, is equal to angle EBD. And the reason is because they are opposite angles. Okay, we got those. And then I'm looking at this, and when we see these parallel sides, we're kind of happy about that, because we know that there's going to be a ton of angle properties invested here. Yeah? So, notice this. We have this Z pattern that's happening. We call those alternate angles. So we can say angle EDB, or actually we started with the ABC over here, so we can say ACB. Really when we say ACB, we're talking about angle C, is equal to angle EDB. And that's alternate angles. So I suppose we could say, okay, therefore, triangle ACB is similar to triangle EDB because of angle-angle similarity. Good with that? Really, just looking for two equal angles. Okay, how can we conclude that these are similar? Triangle RST is similar to triangle JKL. See, in this situation, you have no angles. We're like, oh man, no angles. No problem. Let's look for corresponding side lengths, and I like to pull out a highlighter when I do this. We know RS corresponds with JK. We know ST corresponds with KL. We also know TR corresponds with LJ. I love to highlight it first. If I don't highlight it first, it messes me right up. So again, I'm going to keep, just so I remember this, I'm going to keep triangle RST on the top and triangle JKL at the bottom. That has to remain consistent. So RS is where I'm going to start because it's the first two letters, right? RS. So RS corresponds with JK. So we say RS corresponds with JK. We're going to create a ratio out of those side lengths. And then if they're similar, they should all be equal. So we're going to write equal to ST corresponds with KL. All right, the green ones. And that ratio should be equal to TR, that corresponds with LJ. I mean, some people might say, no, this is side RT, not TR. And I'd say, okay, sure, it's not a big deal. I like to just go in that triangular motion. Now what we're going to do is fill in the blanks. RS is really 12, JK is really 4. All right, ST is 15, KL is 5, TR is 18, LJ is 6. What we want to do next is reduce these as much as possible. So we'll end up with 3 over 1, 3 over 1, and 3 over 1, which is kind of nice because we can say that, well, all of the ratios of the corresponding side lengths are equal, or rather, they're in proportion. So therefore, they have to be similar triangles. So therefore, triangle RST similar to triangle JKL because of side, side, side similarity. All three sides, you can see that there's a scale factor of 3. Now, in this example, it's blatantly obvious that it's 3. Again, I want to remind you in the future, it might not be as obvious. Okay. Are these triangles similar or congruent? And how would you know? What do you think? If I look at all three of these, I go, okay, this one has 2, this one has a 2, this one has a 2. Okay, they all have a 2. How about a 3? 3, 3. And how about a 4? Yes, a 4 and a 4. So because all of the side lengths are quite literally equal to one another, they have to be congruent. They have to all be congruent. Congruent because all corresponding side lengths are equal. Like there's Sure, some people might say, well, there's a scale of 1. It's like, okay, yeah, sure. But it's quite literally the same triangle 3 times, maybe rotated a little bit on each kind of one here. Okay. Folks, I assigned here 1 to 5, and then 9 and 10 on 378, 381. I know we went right to the wire here. Let me turn this off, and we can chat about.